If you look around at the horizon, there's nothing there to mark north, south, east, or west. And yet, people around the world all came up with at least 4 cardinal directions. How did they do it?
You might think of the North Star, but fun fact, the Earth's axis didn't line up with the North Star until after the fall of the Roman Empire. You might think of sunrises and sunsets, but the sun hardly ever rises due east or sets due west. It just rises, mostly east-ish. Very imprecise. The only reliable marker of any of the cardinal directions was the sun, which was due south at its highest point in the sky every day. But how is that helpful? How do you know exactly when the sun is at its highest point of the day?
Okay, here's my idea. If I put a stick in the ground and watch the shadow all day long, the direction of that shadow will change as the sun moves across the sky all day. And that shadow should also get shorter and shorter all morning as the sun rises, and longer all afternoon as the sun sets. The shortest shadow of the day should happen exactly at noon, that moment when the sun is highest in the sky. At that moment, the sun should be due south, and its shadow should point due north. The tricky thing is figuring out exactly when that moment is. But if you have a shadow from the morning and a shadow from the afternoon that are exactly equal in length, then the direction of the shortest shadow should be exactly halfway in between them. Here we are at the local park and ride where I can set up something with plenty of sun. So here's my gnomon, just a stick basically. And so I'm going to use my sidewalk chalk to mark the tip of the gnomon's shadow where it is right now at 10:15 in the morning. I'm going to leave this set up over the course of the day, and I'm going to come back and visit it now and then. But I'm also going to draw a set of concentric circles around the gnomon using some string and some chalk. That shows the distance from the gnomon of that 10:15 mark. We'll come back to check the shadows in a little bit. Okay, things are looking good. It's very sunny still. Everything seems intact. You can see that the shadow has definitely moved since last we were here at 10:15. It's almost exactly 2 hours later, 12:15. Let's mark it. This pink color to denote the length of the shadow. I'm going to do another concentric circle here. Whew, it's hot out there. So I've been marking the time. But the people who first did this, not only did they not have clocks, they probably didn't even have hours and minutes, the idea of measuring time like that. So this can work just fine without marking the time. I'm doing it more as a convenience for us. All right, speaking of time, it's almost local solar noon. So time for us to get back over there and make another mark. We're within just a few minutes of solar noon, which means that this shadow is the shortest that it will be all day, with the sun as close to directly overhead as it will get. Now, of course, the ancients wouldn't have known exactly when solar noon was until they did an experiment like this. So I'm marking now the tip of the shadow, which is just to the inside of our concentric circle, 12:53. Because the shadow at 12:53 is not that much shorter than the one we measured at 12:15, it's gonna be hard to tell exactly at what point we should take our next measurement, because the shadow's kind of skimming along the inside of that circle. I guess what that means is that I'm gonna have to rely on my outer arc. It's kind of amazing how much you can see the shadows changing once you mark them, right? I just marked this at 12:53, and it's now only 3 minutes later, and I can see that the shadow has moved. It's about 1:15, and I'm gonna wait a little bit longer to call it, because it looks like it's closer to the inside of that line than it does to the outside. I'm gonna try and wait until it's feeling like it's right in the center. Yep. And there goes the sun. So it might not even have a shadow in a few minutes. I guess we'll see. Well, it's a few minutes later, and the sun is definitely behind a cloud. I am going to wait, perched here with my chalk, in hopes that some shadow appears in a crack between the clouds.
Oh, almost. There it is. I'm gonna call that. That looks pretty good. So now we have 2 points on the same arc, equal distance from the gnomon. If we're right, those 2 points should be on an east-west line, and perpendicular to them should be a north-south one.
This has been the sunniest day in like 2 weeks, and still the clouds are thwarting this project.
However, I got a measurement within a few minutes of my shadow crossing my first arc, which I started at 10:15 this morning. So now I'm trying to set up a straight line between my mark at 10:15 this morning and my mark at 3:20 this afternoon. Okay, I feel like that is about as straight a line as I will be able to get. So, theoretically, that line is east-west.
Okay, so here's the next thing. If we have an east-west line, north and south should be perpendicular to it. But there aren't a whole bunch of right angles out there in the natural world. So how did the people of ancient times figure out an accurate north-south line from this east-west one? There's a couple different methods that someone who's taken some high school geometry might know, but here's the one I think would be most intuitive to our ancestors. Check it out. I'm going to take a string and cut it to the length of my east-west line. This is the length of my east-west line from point to point along that arc. And that's half of it. So this should give me the other point besides the gnomon that draws that north-south line. Let's check it out, see if it works.
It doesn't look perfectly square to me.
We can check it another way.
Tie a little taut line hitch in the end here. I'm gonna mark that point with a little knot to make sure
That I'm doing the same length on both sides.
all right, here goes nothing. All right. You can see that that pink line's off a little bit from the yellow one.
I wonder if any of them happen to be north, south, east, or west. All right, now it's time for the real test. Let's go grab the compass.
We're gonna set it to 346. That's the declination for here in Putney.
And we'll see
If this line,
actually matches up with true north.
I'm a little nervous. Here we go. Let's see.
Well, it looks like we did it. That was fun. My sun compass was accurate to within a few degrees. But for me, building that sun compass raised new questions. If finding directions is so tricky and it takes all day to do it, then why did ancient people bother? When I started this project, I assumed that people invented directions to help them find their way, to cross mountain ranges and navigate through forests. But after building that sun compass, I realized it's totally impractical. It makes me think that ancient wayfinding probably wasn't directional at all. It was probably relational, based on concrete things in the landscape like uphill or downstream or along the shore or follow the ridge. I now think people probably found their way because they just knew the land. They had a map in their head and they had memorized millions of places. So if it wasn't for navigation, what were the cardinal directions for? After building the sun compass, I've come to think that probably people invented the cardinal directions to survey land. The oldest civilizations were all along rivers that regularly flooded their banks, and in the process probably erased any boundary marker or property line. To reestablish those boundaries required something that wasn't based on the landscape, that wasn't based on something that the rivers could change. So my new idea is that these cardinal directions probably didn't arise until people were living in cities that required a great deal of coordination. Having a way to define a place that didn't rely on landmarks must have seemed powerful, almost magical. And the sophisticated math that it took to do it probably seemed a little bit like sorcery. The fact that today I can know them in an instant, and for any place on the planet, it's kind of a miracle.